All right, thank you, Andreas. First of all, I'd like to thank the conference organizers for inviting me to give a talk here. It's a great opportunity. I'm very happy to be here. So I'm going to talk about extinction time and maximal displacement of critical branching Q-Levy processes. There are a lot of terminology there. I'll try to explain as I go along. Okay. So this talk is based on a joint paper with Hao Jiehou, Yan Xiaoren, and audience, and basically the same title. Okay, it's available on the archive and also on our home pages. Okay, so I'm going to talk about critical kill branching Levy processes, but let's first start with branching Levy process first. Okay, so most of you guys are familiar with this, but I'm going to start from the beginning. Okay, so a branching Levy process on the real line can be described as follows. So initially, there's a particle at a certain site x, and this particle moves according to a Levy process starting from that point. Okay? And after the exponential time of parameter beta, and for this exponential running variable is independent of the spatial motion, this particle dies and split into k offspring with probability pk. So there's a random, there's offspring distribution, and then each of the offspring independently repeats its parent's behavior from the death place of the parents. And this procedure goes on. Okay, fix the time t, and then use nt to denote the collection of particles alive at time t. And for any particle u alive at time t, we're going to use xu to denote the position of u of that particle u at time t. That's the usual standard notation. And for any time s less than t, and for the particle u may not be alive at time s, but either that particle is alive at time s or one of its or its ancestor will be alive at that time. So we're going to use xus to denote the position of u or its ancestor at time s. Okay? And now look at time t, collect all the particles alive at time t, look at their position, you're going to form a point process. We'll call it ZT, and this ZT is called the branching Levy process. Okay? And the standard notation is going to px denote the law of this process, and sometimes you use just p to denote if the initial particles start from origin. Okay? Let m be the mean number of offspring. Okay? Of course, then the branching Levy process is going to call it supercritical if the mean number of offspring is strictly larger than 1. And if the mean number of offspring is equal to 1, then we'll say the branching Levy process is critical. Otherwise, it's going to be called subcritical. And of course, it's well known that the branching Levy process will become extinct with probability 1 in the critical and subcritical case. Okay, so in this talk, we are mainly interested in the critical case. That is, the mean equal to 1, of course, excluding the trivial case, p1 equal to 1. Okay? So for any time t, let mt to denote the maximal position of all the particles alive at time t. And because we're dealing with the critical case, you can define the maximal displacement, the all-time maximal displacement. And also we're going to define the extinction time this way here. So that's capital M is the maximal, the all-time maximal displacement. Zeta, of course, the usual notation for the extinction time. And because we're dealing with the a critical case, you know that the all-time maximal displacement is always finite, and for the lifetime is finite. Okay, will be, of course, our focus is not on critical branching Levy processes, but let me review a few results on branching Levy processes. And of course, in this case, our branching rate is always beta, and the offspring distribution is spatially homogeneous. It does not depend on spatial location. So the lifetime zeta is basically the same thing as the extinction time of a continuous time Galton-Watson process with the same branching rate and same offspring distribution. So in this case, the decay rate of this extinction time is well known. Okay, but just for the sake of it, let me recall what it is. Okay? Under the assumption that offspring distribution belong to the domain of attraction of an alpha stable distribution, or more precisely, so here is, there is an alpha strictly between 1 and 2 at a constant kappa alpha positive, such that that limit is equal to kappa alpha. So that's basically saying that the offspring distribution belong to the domain of attraction of an alpha stable distribution, or in the case alpha equal to 2, it's basically assuming that the offspring distribution have finite second moment. Okay? So that's alpha strictly between 1 and 2, or alpha equal to 2. So under this assumption, and of course it's well known that the tail of the lifetime extinction time behave like t to the minus 1 over alpha minus 1. And of course in the case alpha equal to 1, it's basically 1 over t. Okay, this is well known, classical result. Okay, and the tail probability of the maximal displacement m has been intensively studied in literature. Maybe I should say a few words. This talk is mainly concentrated on the critical case. In the supercritical case, of course, there have been a lot of studies on the behavior mt. That's the asymptotic behavior mt at t equal to infinity. A lot of people in the audience have made contributions, but since I'm interested in a critical case, I'm now going to review the literature in the supercritical case. So there's a lot of connection with FKPP equation, all those sort of things. But in the critical case, it's more interesting to study the all-time maximal displacement. Okay? So in this case, already in 1979, Sawyer and Fleischmann proved that under the third moment condition, and when the spatial motion is a standard Brownian motion, they proved that there exists a constant theta, such that basically saying that is the tail of this all-time maximal displacement is of order 1 over x squared. Okay? Okay, so this is the case when the third moment is finite and the spatial motion is a standard Brownian motion. And in the case of critical branching Levy process with offspring distribution still satisfying the third moment condition, but a more general replace Brownian motion by more general Levy processes. You can see the paper by Lally and Shao, and also 2 papers by Perfetta. Okay, so so those are the. I'm not going to review those things here. I'm going to state more general results. So this is under the third moment condition on offspring. In the case of critical branching Levy process with offspring distribution, belong to the domain of attraction of alpha stable distribution, or more precisely under the assumption H1 as stated a little while ago. The following, and also the following assumption on a spatial motion. So we need some assumption on a spatial motion. So the first assumption on spatial motion is that the mean is 0, and find the second moment. Okay, and we need a little more assumption on the on a spatial motion. Also, we're going to assume that the positive part of C1 has finite R0 moment where R0 is large enough. Okay, of course, in the case when alpha equal to 2, that's simply you're going to assume R0 larger than 2. So a little bit higher than second moment, but this is only on the positive part. Okay, if you have spatially negative, then this condition, of course, will be satisfied automatically. Okay, so under H1, H2, H3, in this paper, joint paper with Hao and Yiyang Jiang and Yan Xiaoren audience, we prove that in this case, the tail of this all-time maximal displacement behave like x to the minus 2 over alpha minus 1. Okay? So here that's our assumption on offspring distribution is weaker, and basically in the domain of attraction of alpha stable distribution, and those assumptions on the spatial motion, we have the tail behavior of the all-time maximal displacement. Okay? So those are all about the tail behavior of extinction time and maximal displacement of branching Levy process. Okay? In this talk, I'm going to be talking about those things for critical killed branching Levy processes. So let me introduce that model now.
Can I just check?
Sure. Yes.
H3 means R0 has to be bigger than 4, right?
Oh, yeah, 4. Sorry. Yeah.
But the other result was the previous result.
That's Brownian motion.
Yeah, but alpha.
No. There's offspring distribution satisfy third moment condition. So this is on a spatial motion. Yeah. Okay, so remember we're dealing with a critical branching Levy process. If in that critical branching Levy process, we kill all particles along with their potential descendant once they exit the positive half-line. Okay? And then of course we obtain a new point process. You basically look at all the particles which are alive at time t but have never reached the at or below 0. And you collect them all together, you call it ZT positive half-line. And this point process is what I call in the title called a critical branching kill Levy process. Okay? So basically saying critical means that the offspring distribution is critical. So the mean is 1, but the spatial motion is basically branching kill Levy process. Okay, and for this critical branching kill Levy process, you define the, okay, so this would be the maximal displacement at time t, and then you define the maximal displacement of all time. And obviously this is going to be smaller than the without killing. And same thing for the extinction time. Okay, so the main concern of this talk is going to be about the tail behavior of this all-time maximal displacement and also the extinction time. Okay? Okay, when the underlying motion C is a standard Brownian motion, Lally and Zhang proved that, again, under the third moment condition, the tail behavior of the all-time maximal displacement behave like 1 over x cubed. Okay, and the limit is in terms of a certain constant times y. Okay, and here I wrote down theta depend on 2 here because later I'm going to assume that the offspring distribution satisfy is in the domain attraction of a stable motion alpha. So in our case, 2 will be replaced by alpha. But here, of course, you don't have to write down alpha, but later alpha going to appear, so that's why I wrote down the 2 here. Okay. Then, of course, you compare this with the case without killing. You can see that both are under the assumption that the offspring distribution has found that third moment. In the case when there's killing, we have this power will be 1 over x cubed. In the case when there's no killing, the power is 1 over x squared. And of course, you can see that the killing plays a role. Okay? So this is Lally and Zhang's result. And Lally and Zhang also show that another result showing that there's a continuous function theta t depend on distribution a parameter y, which is between 0 and 1. So instead of starting, so previously, the starting initial position at y, that's fixed. Okay? Then you let this level go to infinity. You have to study the tail behavior of that guy. So they also prove that when you start from, instead of starting from y, you start from x times y, and then the level is x. Then in this case, you have x squared times this guy here goes to that limit. Okay? So if you look at this guy here, if you start from a fixed point y, let x go to infinity, you have x cubed. And now if you start from x times y, so the position also go to infinity, the starting position also go to infinity. In this case, the tail behavior again reverts back to 1 over x squared. Okay, so of course so this is the case when the spatial motion is Brownian motion. And of course, in the case when the spatial motion is Brownian motion, the generator is basically a Laplacian operator, or in that case, a lot of you can do exact calculation. In fact, the argument of Lally and Zhang relies heavily on the construction of that guy here. You can basically write down the differential equation for that, and the solution can be given by the so-called virtuous P function, at least in the case of binary branching. And for general branching, they basically do kind of comparison argument, then get their result. So in this case, their argument basically they can do, at least in a special case, you can do write down somewhat explicit result for the interested quantity. Then for a little bit more general case, they do a comparison argument. And of course, we're interested in the case when a spatial motion is Levy. In those cases, it's impossible to do exact calculations. Okay, so those are the review of the existing result. Okay, basically under the assumption that the spatial motion is Brownian motion and offspring distribution satisfy the third moment condition. Okay, we're going to try to weaken the assumption on the offspring distribution and also generalize the spatial motion from Brownian motion to Levy processes. Okay, so we're going to assume a little bit stronger condition than H3. Remember, H3 was a moment condition on the positive part of the Levy process. We're also going to have the same condition on the dual that guy. So we're going to replace, in some result, going to replace H3 by H4. Okay, basically assume that the absolute value of the Levy process satisfy that moment condition with R0 satisfy the same condition. Remember, the alpha is we're assuming offspring distribution is in the domain of traction alpha stable. So this alpha is the same thing in H1. Okay? So to state our result, we introduce some notation here. So of course, that's the standard notation for us dealing with our Levy process, tau x plus. So the first time it goes above x, the Levy process goes above x. Tau x minus, the first time it goes below x. And under condition 2, you can easily check this C of tau 0 minus, the absolute value of that is positive, the finite. Okay? With that, we can introduce this quantity R of x equal to x minus that's the mean position of when you first exit the positive half line. Okay? And you can rewrite it a different way. Basically the same thing, you can easily see that. Therefore, you can easily see that R of x is always large equal to x. Because you're starting from x, you're going to go below the origin. So you're going to be R of x is definitely large equal to x. And the function R will be non-decreasing harmonic with respect to this stop process. And of course, in the case when z is Brownian motion, this R of x simply equal to x. Okay? And this function R, you're going to appear in our statement of our result, in some of our results. Okay? And also, not only we're going to try to get our result, some of the result we're going to try to give probabilistic interpretations. And so some of the limit in our main result will be written in terms of a super process. Okay? So we're going to try to give some explanation of this probabilistic interpretation of our limit. So involving a super process xt with spatial motion W0, that's going to be absorbed Brownian motion. So your Brownian motion hit 0 or below, hit 0, you stopped it. Absorb Brownian motion, stop Brownian motion, and the branching mechanism of this super process will be this guy here. Okay, this depends on the domain of traction. Remember, our offspring distribution is in domain of traction of a stable process, a stable distribution. So this offspring distribution, or the branching mechanism, our super process, depend on this alpha. Here, this kappa alpha is the kappa alpha in H1. And of course, in the case when alpha equal to 2, this is basically dependent on offspring distribution. Okay? So we're going to make connections with a certain super process and the branching mechanism of the superprocess is given by this guy here. So this is connected to our assumptions. And of course, even though we're starting looking at branching Q-Levy processes, our Q-Levy process higher than second moment. So in the limiting result, we're going to get branching Brownian motion. Okay? So let me say a few words about this super process. I'm not assuming everybody's familiar with this, so let me quickly go over that. So for any finite measure on the positive half line, so the super process X is in finite measure value process, Markov process, such that is log Laplace function, or it's given in this form. So for any bounded positive function, you do the integration of f with respect to this measure. You exponential of that, take the expectation. So basically, that's the log Laplace function, or is given by this function. This integration, the initial measure against a certain function, where this function is the unique locally bounded non-negative solution to that guy here. So here, of course, that's the spatial motion, or absorbed Brownian motion, and that's the branching mechanism that appears. Okay, this is the our superprocess. In general, of course, superprocess, if you're not familiar with superprocesses, superprocess can be regarded as certain high intensity scaling limit of branching Markov process, branching random, thing like that. So although this is not very intuitive, but it can be, just like Brownian motion can be obtained as scaling limit of random walks, this branching, this superprocess can be obtained as high intensity scaling limit of simpler models. Okay? And without loss of generality, I'm going to assume that our superprocess is canonical. It's basically defined on this path space. Okay? That's all the Cadillac process taking values in here. Okay? And also, I'm going to use another notation here because some of the limit will be expressed in terms of the excursion measure or end measure of a superprocess. That's why I'm going to spend a little time on this guy here. So we're going to use W0 plus to denote family of all the this Cadillac value function taking values here, but only defined on the strictly in the positive half line, and with 0 as a trap, and with the limit at 0 being 0. Of course, you can regard this as a subset of this path space, but that's technicality. We don't have to worry too much about that. So what I'm trying to say here is, for our superprocess, there exists a unique family of sigma finite measures ny for all y's in a positive half line on this space here, such that for any finite measure mu on R plus, if this script calligraphic n is a Poisson random measure on this space with this intensity, then you can define such a process here, x0 hat equal to mu, xt hat equal to this guy here. Then this will give you a realization of this original superprocess. So for those of you who are not familiar with this kind of this kind of measures, you can think of this as, in some sense, this superprocess kind of infinitely divisible. So this excursion measure can be regarded as somewhat, in some sense, the Levy measure of those things here. Okay? So these measures are, in general, not probability measures, they're sigma finite measures. Okay? So those concepts, this superprocess and excursion measure of the superprocess will appear in our limit. Okay? That's why I'm spending time going through those notions. Okay? So put them all together, those are called the end measures of our superprocess, or the excursion measures of our superprocess. Okay? And now remember, our superprocess can live on the positive half line, including 0. So I'm now going to restrict those measures strictly in the open half line. And this is what I call a critical super Kilbarn motion. So now the state spaces of our measures, the open half line. Okay? Okay, so this is our first result. Yes. So here we're going to assume H1, H2, H4. So remember, H4 is a little stronger than H3. So here is for any y positive, if you look at the tail of this extinction measure, but if you start with square root of y, and then let t go to infinity. Then in this case, the tail is basically, well, minus 1 over alpha minus 1. And also, now we have this basically, the decay rate is 1 over that, and also there's a probabilistic interpretation of the limit. Okay? And the probabilistic interpretation limit is in terms of the excursion measure of that superprocess. Okay? So this is when you start, when the start initial position also moves with time, moves away from the origin. And if our initial starting point does not change, you only let the level set go to infinity, then the tail behaves like 1 over that guy. Okay? In this case, the limit involves our harmonic function r. Of course, in the case of Brownian motion, this ry simply becomes 1. Okay? So the tail behavior, that's the things about the tail behavior here. Any questions? Okay, and if you take a look at that guy, if you, for the case of a critical branching Levy process without killing, the tail was 1 over that. It's basically that's it. We have seen that before. Without killing, that's what is it. But for branching kill Levy process, if you start with a fixed position, then behave like this actual decay. While if you start with this position that square root of t times y, let t go to infinity, then the tail behavior reverts back to the original one. In some sense, you can interpret this because our spatial motion is basically has high moment condition. So basically, it's in some sense, behave like Brownian motion. So if you move the initial position according to square root of t, you do not feel the effect of the killing too much. That's why in this case, when you start from here, and the case without killing, it's basically the tail behavior is more or less the same. At least you can think of it that way. Okay, so that's our first result on the tail on extinction time. And also I'm going to talk about some kind of scaling limit. So fixed for any time t, we define the following scale version of our branching kill Levy process. So we're going to scale position by square root of t, and then do some normalization here. Okay? So then the next year we're going to talk about the limit of this guy here, the limit of the scale process under this conditional laws. So this would be both under that the survival time is larger than t, the extinction is larger than t, and one result is about initial position square root of t times y, the other one is y. Again, the result will be a little bit different in these two cases. Again, our assumption is h1, h2, h4. So if you start from square root of t times y, then under this condition, this scale process, again, the limit written, the limit return in terms of our superprocess. Okay, the excursion measure of our superprocess here. On the other hand, if you start from the position, initial position fixed, then the limit is not related to the superprocess, but in terms of a certain random measure in that way here. So depend on if this is your initial position, this one interpretation of the limit, otherwise that's the interpretation of the limit. Okay? So in this PTR paper of Alan Powell, she studied the critical branching diffusion processes upon first exiting a bounded domain, a smooth domain RD. And there she proved that there's certain scale limit under this assumption here. Okay? The process hasn't become extinct at time t. Okay? This converted to a certain exponential random variable. So this is the key assumption there is the D is a a bounded smooth domain. So basically, the spectral decomposition of those semigroups play an important role, things like that. So the argument there doesn't work if D is unbounded. So in that paper, Alan asked a question of what happens when D is unbounded, right? And of course, we couldn't answer that question in a general case for general high-dimensional cases, but what it did, our theorem 2 answered this question in a case when D is the positive half-line. Okay, if you scale it properly under that condition, there's certain scaling limits. Okay, so that's our second result. Okay, and so now going to talk about result on the all-time displacement for branching Q-Levy processes. Okay, and now going to define this the all-time maximal displacement for killed super kill process. This is basically our killed super Brownian motion. Okay, so this branching super process with the spatial motion being the absorbed Brownian, killed Brownian motion. So we're going to define this guy here being the all-time position of that super process. Okay, and now here is our result. Okay, so here again H1, H3, H4. If you fix y, if you start from xy, then you let x go to infinity. Then remember, this guy here is the all-time maximal position of our branching Q-Levy process. And on the right-hand side is written in terms of this super Brownian motion. Okay, this is x here. That's written in terms of this. That's super Brownian motion. So this is all-time position of a super branching Q-Levy process, and this is for written in terms of super process, super Brownian motion. Okay? So when you start from x times y, you let x go to infinity. Okay? And for the next result, I'm going to make H4 a little stronger. Remember, H4 with R0 larger than 2 alpha over alpha minus 1. If you assume this R0 larger than 1 plus that. So of course, in the case of Brownian motion, instead of larger than 4, you're going to be larger than 5. Okay? Then in this case, then if you start with a fixed point y, so this y doesn't change, then if you look at this is 2 over alpha minus 1, here will be 2 over alpha minus 1 plus 1. In this case, you have a limit, the tail behavior. So this is when the initial position changes, you have one tail behavior. And when initial position doesn't change, you have a different tail behavior. And of course, here the limit is written in terms of the super Brownian motion. Here, the limit is written in terms of this harmonic function.
You can't write the right-hand side of 12 in terms of excursion measure?
We didn't, well, you control, but it's more convenient to write it this way here. Well, both are related to the super Brownian motion anyway. So whichever is more convenient.
That's a multiplicative event.
Yeah. You can think of it that way also. You can try to do it that way. But this is a neat way of writing it, we think. Yeah. Okay? So that's our third result. Any other questions? Okay? So when R equal 2, the first result is consistent with the result of, I think it's 7 is Lally Zheng. And the second result is also consistent with what Lally Zheng proved in the case of branching Q-Levy Brownian motion. But of course, their offspring distribution satisfy the third moment condition, also of course dealing with spatial motion being Brownian motion. Our offspring distribution is weaker. In some sense, our offspring distribution, assumption offspring distribution is optimal. Okay, as I mentioned before, Lally Zheng's result, that constant in their result are given in terms of more or less in terms of Weierstrass's p function. Our limit is given in terms of the super process or in terms of the harmonic function R. So we have, in some sense, at least in the case, in this case, we have a probabilistic interpretation of the limit also. Okay, that's already mentioned. This mentioned before. Let me. When you have kill, the tail behavior a little bit different. You have some extra -1 there. Paying attention to that. Okay, one more result. So the following result gives a Yaglom time limit for the all-time maximum position. So define such a quantity there. Then under H1, H2, H4, so this is the scaling limit of this maximal position at time at time t. This is the branching Q-Levy process, and the limit is in terms of our excursion measure, our super Brownian motion. So this is, again here, this is the starting position square root t times y. And if you start with it y here, then the limit will be different. Interpreted it. Okay? So both of these can be regarded as some kind of Yaglom time limit for the scaling limit for the maximum position at time t. Okay, so let me say a few words about the main ingredients. So I'm actually going to give you the main idea of the proof of theorem 1. Just briefly sketch it. Okay? So what we do here is we want to somehow make the connection between our branching Levy process with super Brownian motion. How do we come up with that connection? So what you do here is you define such a quantity here. Okay? For example, you define such a quantity here. Remember, that's the branching Q-Levy process. Critical branching Q-Levy process. You can write it this way. That you can write this either that or in terms of the, remember theorem 1 about extinction time. So read a certain scale version of extinction, tail of the extinction time, call it V infinity t, and you define another quantity for this maximum position. Okay? Then actually for theorem 1, we're mainly interested in that guy. So basically, what you do here, we first derive an integral equation for that quantity. And you can also derive integral equation for that. Okay, that's relatively straightforward. Then of course, we're going to derive, under our assumption on the spatial motion, we can get various exit probabilities of the underlying process. And here, the harmonic function R will appear, and also certain limit theorems. For example, we're going to use some result from Grandma and Shao, with the paper going to appear in Henry Pankari soon. Those will play a role here. Then use the result of A and B and the Feynman-Cast formula, we can prove some analytical properties of this quantity we defined. And then we show that there's a limit when t goes to infinity. And of course, first we're going to first show that is along at rational points, you can get the limit to exist using a diagonalization argument. Then by using those various properties, you can show actually this limit indeed exists. And then we show that the limit satisfies, solve the certain initial value problem of certain differential equations, and that differential equation is connected with superprocesses. And because that initial value problem has a unique solution, we know that quantities involved in super Brownian motion is a solution. The guy we constructed is also a solution, so therefore you have a probability interpretation of that quantity. And from there, you get a result. Okay, thank you very much for your attention.
Okay, there we go, first question.
Yes, so about your proof, so the proof sounds very analytic, right? So
Pardon me?
The proof sounds very analytic. So could you have a more probabilistic proof using, for example, so the fact that so the super process is the scaling limit of, so this will yield probably a lower bound for the tail of the maximum?
Yeah, we haven't thought about that way, but here that, yeah, in some sense, yes, our proof is more analytical in flavor. So it will be interesting to give a more probabilistic proof. So I haven't thought about that. That'll be an interesting question to look at.
Because relatedly, in discrete time, for example, if it was a discrete time,
in something you cannot get the result in something directly from, even if you have a similar result for discrete time, when you take the limit, the quantities are not going to be continuous. So it's difficult to argue for direct from the discrete time to continuous time. You can think of it that way, but there's also some subtlety involved, I would say.
Any more questions? Sandra?
So in your limit, you have a super Brownian function. So I will guess that it will be a super Levy process, so then you will still have jumps. Can you say why?
No, here is because because we got a super Brownian motion, because our assumption of simple motion is has more than two moments. So if you, for example, if the spatial motion is Levy process, then things will be different. Then you might get a super Levy process. But because our assumption of spatial motions have more than two moments, so in the limit you're going to get Brownian motion. Yeah.
Can I ask my question anymore? Okay. To continue from Pascal's question. So I'm pretty sure everything you've done will still work if, instead of locally birthing the offspring, if you scatter them on a point process. So if you happen to scatter them all below the origin, that's just adding an additional jump onto the Levy movement.
Could you repeat? Could you repeat?
So when you give birth, you put all the children in the same place.
Yeah.
So you could put them on a point process, and I think everything.
Yeah. So basically, okay, that's more closer to the topic of this conference, non-local branching.
Exactly.
Yes. Yeah.
So I was going to say you have to do it all again.
Yeah. Yeah. I was going to start up to apologizing that in non-local branching we have our branching local.
So you'd have to replace your H4 moment with a kind of a spatial moment on.
So there'll be some of the idea will be similar, but there'll be more work to be done. It's definitely worth doing.
Okay.
Yeah.
Do it. I mean, it's
okay.
well worth it. Yeah. Okay. Thank you very much.
All right. Thank you.